We have a good turnout today for our webinar. Thank you so much, everyone, for joining us. I'll get started with introducing today's webinar topic and then our wonderful panel that we have here today of experts that are ready and willing to address your questions. So today's webinar is on open pit slope design, specifically slope characterization models, those being the geological, structural, hydrogeological, and rock mass models that are used to then filter into the geotechnical model for an open pit slope design. So our experts here today, they have a varying range of expertise within these topics, and they are all suited to answering your questions on any of these different type of site characterization models. And this is an Ask the Experts webinar, so it is interactive. We will be accepting questions throughout this webinar, and in just a moment, I'll tell you how you can submit those for our panel. And we have this webinar set to run for 90 minutes or until we run out of questions. And today's webinar is brought to you by the Geotechnical Center of Excellence, located within the University of Arizona here in Tucson, Arizona. We are an industry-funded and member-led center. We work interdisciplinarily to produce collaborative geotechnical research and educational projects with the goal of bridging gaps within and between academia, industry, and fields of study. If you're interested in learning more about the GCE, please send us an email at the address shown on the screen or reach out to any of the team members that are here today that I'll introduce. And the topic of this course is related to one of our current professional development courses that's running online right now. It is currently open for registration, and it is on fundamentals of open pit slope design, containing all of the subjects that you see here. You can register for this course either by scanning this QR code here, or I believe one of my teammates will be posting a link in the chat, so you'll be able to click that and learn more. And if you go to our website, you can also find a flyer depicting more information on the course and send us any questions that you have to the GCE email. And we want to acknowledge our membership. They are the ones who make courses like this possible, webinars like this possible, who support our research and our team. The GCE members range from executive level to partnership members. They are involved with supporting our research, supporting our courses, funding our staff, and many of them who also contribute as expert presenters and panelists and research advisors in our many projects. So we want to thank them all very much. Without you, we could not be doing what we're doing, so we're very grateful for your support. And this course is based on a textbook that was produced by the Large Open Pit Project, which is the Guidelines for Open Pit Slope Design. This text is currently being updated and will be released with an updated version soon, but you can access the original version, which was produced in 2009 through lopproject.com, and you can look forward to an updated version of that book coming soon. And now to introduce the team that I have here with me today. I am Jillian Noonan. I'm Senior R&D Engineer with the GCE, and I'll be your moderator today. And then along with me, I have some of the GCE team, including Julia Potter, who's the director. Julia, thanks for being here today.
Thanks, Jill, and hello, everyone. We're looking forward to a great discussion.
And Benjamin Meyer. Benjamin is a software engineer for research and development with the GCE. Thanks, Benjamin.
Thanks, Jill. Hi, everybody. Welcome, and we're glad that you joined us today.
And Cheryl Bukowski, who is fairly new to the GCE, is our professional development program lead. And we're really glad that she's joined the GCE and that she's here today to meet all of you and to help with the webinar.
Thanks, Jill, and thanks for being here, everyone.
So this team here today will be fielding the questions that you put into the Q&A and helping to sort those in and send them off to our panel that we have here today. And speaking of our panel, today we have a great set of experts. We have Scott Silwick. Scott is Vice President of Colin Nicholas. He also acts as one of the lead technical advisors for the Fundamentals of Open Pit Slope Design course, and he contributed a course module related to the topic of this webinar, which was on the rock mass model, rock mass strength. Scott, great to have you here. Thank you.
Thanks, Joe. Happy to be here. Hi, everybody.
Next, we have Jeff Beal. Jeff is Global Technical Advisor with Pitot Associates, and Jeff contributed a course module for this section on hydrogeological model, particularly hydrogeology and slope engineering. Jeff, thanks for being here.
Thank you, Julian. Nice to be here and looking forward to some good discussions. Thanks, everybody.
And we have Felicia Weir. Felicia is Director and Principal Engineering Geologist with PSM in Australia. And Felicia produced a module that was within the structural model, focused on structural domains. Thank you, Felicia, for your contributions to the course, and thanks for being on the panel today.
Thanks, Julian. Great to be here. Thanks for having me.
Next, we have Luca Zorzi. Luca is Principal Geosciences Specialist with WSP, and Luca gave us a module on structural modeling tools. Thank you, Luca. It's great to see you again and great to have you on this panel.
Hi, everyone. Thank you for joining, and very happy to be here.
Next, I'd like to introduce Iris Linauer, who is Lead Structural Geologist with WSP. And Iris's module for the course focused on the geological model and ore body environments. Thank you, Iris, for being on our panel today.
Hello, everyone, and thank you for the introduction, Jillian. I'm excited to see what questions come up.
And we have John Fedorowicz. John is a professional structural geologist with John Fedorowicz Structural Geology Consulting. And John gave us a module for the course on the structural model components. Thanks, John, for being here, and thank you for contributing to the course.
Thanks, Jillian, and happy to be here, and welcome, everyone.
All right, well, that introduces our panel today. They are, I'm sure, very excited to address the questions that you will be submitting, and now I will tell you how you can do that. So as an attendee, just to let you know, you are muted and your video is off, so no need to look for those controls. If you'd like to communicate with the panel today and ask a question, you can enter them at any time using the Q&A function, which you'll find on your Zoom control panel. Looks like this button here. So you can click on that Q&A icon, and then you'll be able to type within that box your question. If you have a question that should be addressed to a specific panelist, please include their name so I know who to address it to. The questions can be entered anonymously by selecting a box within that Q&A. And then you also can read others' questions and you can vote for ones that you like. If we have questions that are highly rated, we will select those and bring them to the top of the queue. We are recording this webinar, and later it will be posted to both the course site and the GCE's YouTube page. And just noting here that anything expressed today is intended for educational purposes, and that if you have a need for site-specific professional advice, we suggest that you definitely seek that in addition. All right, and thank you so much for joining us. And with all that, we are ready to get started with our first question. So the way this will go for our panel is I will read out each question, and then I will send it off to one of the panel to start or open it up to the panel to discuss. So this question we are first addressing towards Jeff Beal, and this came in from Jonathan pre-submitted through the GCE email. And Jonathan's question is, in the context of the included site characterization models, being the geological, structural, hydrogeological, and rock mass models, it seems to me that of those four types, the hydrogeological model could vary greatly over time, while the others would remain fairly consistent once characterized. So could the panel please discuss, firstly, if this is indeed the case, and second, how the hydrogeological variations are incorporated into the hydrogeological characterization model. So Jeff, I'll have you start with this, and then the rest of the panel can comment afterwards.
Okay, thanks, Jill. And yeah, I think first start off by saying that of all the parameters and the geotechnical inputs to slope engineering, the hydrology is the one thing that you can change. It's the one thing you can vary. You can dewater the pit. You can depressurize the slopes. And so it's always good to look at that and to think that, how can we change things? How can we improve things in terms of the overall geotechnical model? So yes, it is indeed the case that the hydrogeological model will vary greatly over time. And, in the life of a project, typically, if you're below the water table, you'll dewater it. And so what that means is your pore pressures will drop, your pore pressures will change as you dewater. And if you have specific areas of the slopes which are sensitive to water but don't respond to general dewatering, you can go in and apply specific depressurization measures in those areas, whether that be horizontal drains, local wells, drainage tunnels, whatever it is, to try and improve the stability of the local part of the slopes. And typically, when you look at the options for slope remediation, varying the hydrogeology or depressurizing the slope is usually the most economically beneficial. It's not normally the lowest cost option for improving the stability of the slope. And then as the project progresses, if you're in a gold mine that's 10, 15 year life, if you're in a copper mine that maybe 50 odd years, the hydrology will vary greatly as the pit expands. And one of the things we need to think about particularly in desert environments is, as the pit expands towards the tailings, towards the plant, perhaps towards site facilities, you start to need to think about leakage from those facilities and how that may affect the performance of the slopes. So yes, the hydrogeological model does vary with time. I'll let some of the other guys chip in to discuss some of the other components of the geotechnical model and how they may also vary.
Thanks, Jeff. Would anyone else on the panel like to comment on variations within the other types of site characterization models and how those are addressed? I see Scott, you've unmuted.
Yeah, I think the characterization never ends. I think that was a really good point Jeff made, that the hydro is something that we can actively work on to change as we're mining the pit. The rock strength kind of is the rock strength. We can't change the rock strength. But as we go from scoping level to pre-feas to feas to operations, we're always going to be collecting more data. We're always going to be updating our models. At the beginning, all we have is drilling data. So from a geotech perspective, we might be missing a lot of things like the lengths of certain structures or the things that we can't measure from drill core. So as soon as we get some exposures, now we can start updating the geotechnical model and start modeling lengths. If we have any failures in the open pit, maybe it's on a fault that we didn't know about or wasn't characterized before. Now we can go ahead and update that fault model and then use that going forward for future designs and future pushbacks. So I would say that even though the hydro model may be a little more dynamic than the others, we are interested in updating, recharacterizing, and improving all of the models throughout the whole mine life.
Thank you, Scott. Would anyone else like to contribute to this question? Luca?
Yeah, no, just to highlight what Scott hinted with the continuity length and geometrical patterns between structures as well. As you go and as we have more exposures, then we might actually starting seeing more connectivity or not, as assumed in previous stages, even during operations. So it's always good practice to go back and check, even though it's true that the hydrogeological model is the one that could have the most I use this term, more dramatic changes or possible more dramatic changes over time during operations. But the structural model and the geological model itself also could get substantial changes once we get more exposures. Because one of the things that we're always struggle is continuity and geometrical relationship between structures and their interconnectivity.
And I guess to build on what Scott was saying, I mean, I think as soon as we excavate a pit, we can obviously start to see and map what the rocks look like. But the other thing to think about is the damage zone due to excavation. I think what we've started to call the excavation damage zone, and that's the blast damage zone, and then the zone of relaxation and deformation due to excavating the pit. And certainly in that zone, and we see a lot of the instability develop in that zone, and the rock mass properties will change and usually weaken as we intercept the pit. So that's a dynamic part of the rock mass model as well. And that's I think that's as a community, I think the geotechnical groups are beginning to look at that more and more and appreciate how important it is that the deformation that results from just excavating the pit.
In addition to that, weathering becomes an issue on the scale of how long a pit is operational as well. Rocks that were covered initially, once they're exposed to air and water, can in some cases change relatively quickly, and the weathering will change in the time scale of how long that pit is operational.
Yeah, that's a really good point.
Yeah, it's also the stress release as well for some rock mass units can be quite influential on how it will behave.
And we did get a question on weathering, so maybe we can pull that up and continue that. We have it initially addressed to Scott, but maybe I'll ask Iris to just first potentially also contribute. I'll start with Scott and then see if anyone else wants to contribute. So this question came in, again, pre-submitted, and with regards to the rock mass model, but it seems this could also apply to the geological model. When you're considering the effect of prolonged exposure to weathering, what data is used to determine this degradation capacity for the intact rock mass? And then how is time frame considered for exposure duration in the geotechnical model, I suppose?
Yeah, I think that's a definite issue, and it's definitely a hard question to answer. I can tell you a few of the things that we've tried on projects before to varying success. But just on my experience going out to pits, it's highly variable. As far as I've been to some slopes that are 40 years old, and the benches still look fantastic. There's hardly any weathering to be seen. Everything looks great. So obviously some rock types in some environments, the degradation process is very slow. And then there are some mines that just after 20 years, it looks like the benches are melted butter. And that's just how fast those particular rocks weather in the open atmosphere. And there's two types of weathering that we've looked at. One is just due to normal atmospheric exposure, and the other is due to exposure from PLS fluids in particular. A lot of slopes at the big open pit mines now, they're right below the heap leach pad, where each pushback is successfully mining into the heap leach pad. And so there have been concerns that if any of those PLS fluids are getting into the benches, how is that degrading the rock? In our laboratory, we have done tests where we take samples, expose them to PLS for a certain period of time, usually a week or two, and then do shear strength testing both before and after the PLS exposure. And just like we see in the field, some rock types we found don't have any strength change at all upon exposure to the acid. Others have an extreme change when exposed to the acid, and that would just depend probably on the mineralogy that's seen in that rock. We've also done the exact same thing in the field for some slopes where we have testing from 10, 15 years ago. It's a slope that's below a heap leach pad, drill a new hole, do new testing on the borehole, and compare that to the data from 10 to 15 years ago. and see if there's any change. I've also seen some pre-feasibility sites where there's not a pit yet, where the operator is curious, how will these rocks respond to weathering? And they've actually taken extra core that they didn't need and literally, made a pile of it next to the core shed, and then purposely let it sit out in the elements for a few years. And then same thing, do testing before and after to see what kind of degradation they get. But those are just some of the strategies we've tried to quantify what this effect can do.
Thank you, Scott. Anything else to be added by any of the other panelists? Please feel free to unmute.
Just in general, I think we have an understanding that certain minerals and certain rock types are more prone to weathering than others. Ultramafic rocks, for example, are not as stable at surface conditions as more felsic or silicious rocks. And then there's a large component of weather and climate conditions in tropical environments. So weathering happens at completely different rates than the temperate climates, and areas where there's freeze-thaw cycles also have a larger input on weathering at surfaces.
Good. Thank you, Iris. Luca?
Yeah, just to add on what Iris just said, the alterations and relative age to the mineralization also plays a role as well, and climate too, as Iris was saying. Young magmatic environment in rainfall conditions, you can have weathering that happens at the scale of hours. And you dig your pit, and then in the span of an hour, you're not looking at the same pit. So it's very variable based on where you are in the world, where you are geodynamically, and what type of deposit you're dealing with.
We dealt with one site that would react very quickly within hours. So you had to have logged at the rig and photographed and sampled and sealed up very quickly, because it was highly expansive clays, and so it would all degrade very quickly. And so you have to, depending on your mineralogy, also think about how you're collecting the samples and when you're collecting them.
And just to add on that is something that we need also to keep in mind when we're doing data collection in the field, when we're related to, for example, world that I'm coming from, it's more structures and fault, being ready and readjust the thinking in very like weathering prone scenarios in which what you're mapping might be exaggerated by just pure weathering. Thicknesses of fault zone or shear zones or stuff could be just exaggerating purely by weathering, and it might not be strain induced.
Great. A lot of considerations. All right, if there aren't any additional comments on this one, I'll move on and pull another question. We have quite a few live questions that have come in. All right, I'm going to put John on the spot for this one because it's with regards to your module 3.3 in the course, which is on structural model components. So I'll read the question out, and then I'll give you a chance to address it, and we'll open up to the remainder of the panel for additional discussion. So John, could you define what you call a fracture, structurally speaking, or does every discontinuity fall under a fracture? I find this is usually not consistent. For example, when we say fracture frequency, it essentially is discontinuity frequency. On the other hand, I know sometimes rock have natural fractures, sometimes induced by veins or other processes. Could be healed, infilled, or just open. Any point documenting hairline fracture, knowing fully well that it was most likely exposed by drill action. So is there any point in documenting hairline fractures? And then another point that came to mind was stress release induced fractures. Do you have any expansion on the topic? So I know we had Mary in section, what was it? One of the sections who was talking about discontinuity. She was unable to be here with us today, but John, are you willing to address this question?
Sure. I guess in terms of characterization for the structural model, we define fractures as tectonic features. In other words, they're induced with some tectonic stress or tension, and fractures. Another category of fractures are fractures that are induced by mining. So they're a small, I guess, a smaller subset of cracks that can be produced with overblasting, for instance, and it's necessary in order to have a robust structural model, in order to characterize which are the tectonic fractures and which are the maybe the other set, the induced fractures. And a common method is by whether the fracture is smooth, criteria such as the smoothness of the fracture, if there's some lineations on the fracture that indicate movement. The other sort of characterization would be if there's coatings on the fractures, then they're natural fractures. In other words, they were possibly open at some point and had some coatings precipitated on them. So I guess in order to be consistent, these type of criteria have to be established for the mapping of the benches, and just to continue with the consistency throughout. The veins and other processes, veins are essentially fractures that were healed totally and totally filled. In terms of hairline fractures, if you're talking about drill core, drilling kind of fractures that were mechanical breaks and so forth, there's criteria for identifying those and separating those out from the natural tectonic fractures. If it's in the pit, then if there's induced fractures on a bench at some point, whether it's right near the blasting front or whether it's further up the slope that is indicative of some potential failure and a gradual opening of those types of fractures, those are very important to identify and to characterize. And the fractures that are close to the blasting area, generally they're identified by roughness and the pattern, I guess, of the fracturing. Stress released induced fractures. I guess if the stress is gravity that's driving, then it's the second category of sort of mining induced fractures. We've opened up a volume of rock and there's failure along a portion of a bench that is induced by the opening, by the mining. In terms of other stress release fractures, I suppose if you have an area that's under high in situ stress, you might have some fractures that are induced, and you get that more in an underground scenario than in an open pit. Those are the main things I can think of to answer the question.
Thank you, John. And I'll open up to the rest of the panel if you'd like to contribute. I see Felicia.
John, just for discussion, I know when I'm organizing a logging campaign with drill holes these days, I tend to instruct my team, the geologists, not to log what we think are drilling-induced fractures. Or if you're going to give them a different code, don't call them joints, because you don't want to mix them up with the natural structures, because they will have a different continuity implications. What do you think?
Was that question to me, Felicia?
Yeah, just for discussion, would you normally in a drill core log what you think are hairline or drilling induced fractures? I don't think we would normally.
No, no, definitely. It depends on the scale and the scope of the project, of course, but sort of micro defects are that sort of category. And if there's no continuity across the core entirely, then they're not really a fracture that needs to be logged, I would say. If it's a hairline fracture and if it is characterized by coatings and or some type of little bit of movement, then I would say it's a it's possible, but it all comes down to the kind of the scale of the project and the scale of the information that's needed. You can certainly if you start logging very small hairline defects, you have to wonder about whether they're drill induced or whether they're actually natural. So hairline features can be a little bit of a bit of a hairball, I guess.
Yeah,
We did have that topic come up in our previous webinar also when we were talking about core logging. And I believe Marisol Lario from WSP was talking about that based on her module on core logging. So that can also be referenced as our previous webinar, which is on our YouTube page in that section of the course too. Did you have any additional thoughts, Felicia? I'm sorry, I might have cut you off. No, you're good. Luca, did you have something to add?
Yeah, just a minor thing that it comes down really to semantic in this case here between fracture and discontinuities, that if we go down to the lexical thing. And when in relation to the question about fracture frequency, if we need to consider as discontinuity, just to highlight what John was saying, it all depends on the scope and the size of the problem that you're trying to address. If we're considering open pit designs purposes, for example, then when we're talking about fracture frequency, we tend to define to talk about joints and normally open joints as well. But if we're trying to define, deep open pit slopes like the Chuquicamata, the Grasberg size, then when we're looking into the discontinuity or the fracture frequency, that's when we might try to introduce in the equation even weak veins, so healed features as well, because the gravity and the strain on that slope could induce gravity-related fractures to nucleate and propagate. So you might want to look for what could, weak systems like weak veins and their 3D organization and shape, how they could influence the overall stability of the slope. So it all comes down to really define the problem, define what you want to call them in your project, and then you adjust basically your analysis based on the problem that you want to solve. And I agree with the fact on the mechanical breaks to just not log them, because that's created a lot of havoc if we try to log the mechanical breaks for open pit projects.
Thanks, Luca. And thank you to our live group for this question and for all of the questions. We have quite a few, so I think I'll move on to another. And I just wanted to mention that many of the questions are related to specific modules in the course, so I just wanted to remind any participants in the course that if we do not get to all of your questions today, which we may not due to time, that I would please welcome you to post them on the discussion board on the course site, and I'll make sure to alert the presenter for the specific module to address your question there in writing. Okay. All right, so the next question I'm going to pull up is for Felicia on your module, which is module 3.5 on structural domains. So the question is asking if you could quickly expand on the term cooling joints. What is a cooling joint? What characterizes a cooling joint? Are there any markers to identify or provide context to the term for those of us that may not be familiar? And then also just a nice comment there for you that your presentation was excellent, content, structure, and all around. So that's nice. Thank you.
Thank you. I love the feedback. All right, so cooling joints are formed by thermal contraction during cooling of an igneous body. So you'll tend to find that they are parallel or perpendicular to the igneous body's dip. For example, a dike, a granite batholith, basalt flows, these will have cooling joints that will be distinct from joints in the surrounding rock mass. And so those joints won't continue into the surrounding rock that they've intruded. Columnar jointing is a type of cooling joint, and columnar joints are often complicate drilling and blasting, and so actually understanding their orientation can be quite important. But if you don't have exposures, just having a look at the structure patterns within your igneous body compared to external, you'll likely notice a difference. And so look for joints that are parallel or perpendicular. So, yep.
All right, thanks, Felicia. I think you'd answered that well. Are there any comments from the panel? All right, I will pull up another. Jeff, it looks like you may have just taken a bite, so I'll skip you for now, but I have one for you coming up.
I'm good.
Huh?
I'm good.
You're good. Okay. I'll give you some time because I'll read it for you. So Jeff's module is module 3.7 in the course, which is for the hydrogeological model on hydrogeology and slope engineering. And so this question is on that module. And we did talk a bit about stress relaxation for fractures, but maybe you can just add a bit more with regards to the hydrogeology and slope engineering module relating to blast damage and relaxation damage zones. So could you expand on how relaxation causes fractures to change, and then I guess the hydrogeological implications of that?
Okay, so I mean, I think both blast damage and relaxation causes fractures to open and therefore allow passage of water. In terms of blast damage, I think the mechanical breakage can be very variable, and it can usually affect fractures of various orientations. And I think what tends to happen is you depend on the rock quality. If you have particularly if you have a ductile rock, then you can get a zone behind the pit face, which is more permeable and which may drain more easily. And if you then have a source of water at the top of the slope, such as a leaky pipe or a weathered, saturated weathered zone, the water will often pass preferentially down the blast damage zone in the upper 10, 20 meters and potentially not even affect the material that's underneath. So that's why I think we trying to characterize the blast damage zone is important. Obviously, in the blast damage zone, there's very little confining stress, so any changes in water pressure have a proportionally greater effect they would deeper in the slope, because there's less rock sitting on top of the on top of the fractures. There's less geotechnical confinement. So any change in pore pressure can have a significant impact. And so it's very difficult to characterize because it's so variable. But what I think what we're starting to get a lot of people to do now is just put in shallow holes, particularly in areas where we know there's the slope's susceptible to instability. Put in, shallow holes, which may be 20, 30 meters deep, and put 5 or 6 vibrate wire sensors in those holes and look at how those sensors respond to rainfall events or respond to the passage of water from weathering or from leaky pipes or whatever the source of water is. So that's the blast damage zone. The deeper zone of relaxation or zone of deformation, typically the concern is more related to fractures which are parallel or subparallel to the slope. I think now one of the things that I've noted in the past 2 or 3 years is just the sheer number of instabilities that are related to slope parallel structure. And where you have slope parallel structure and where that structure, the faults dilate, then it allows water to get in. If water gets in, it can actually, in addition to changes in the effective stress, it can actually build up a bit of a driving head. And so if you have, let's say, 20 or 30 meters of continuous head in a fracture that is, let's say, 20 or 30 meters behind the slope, that's a significant proportion of the stress field. And a lot of the instability we're starting to think can occur because of the driving force of the water in fractures that are subparallel to the slope. So I think the blast damage zone and the zone of relaxation, that they're continuous, but I think they need to be looked at a little different, and particularly when you have slope parallel structures which dilate. That is something I think that we, as a geotechnical community, probably need to focus on a little more.
Great, thanks, Jeff. Would anyone from the panel like to expand on that?
I just add one more thing. Thought all Jeff's comments were really good. Another reason to control the surface water and not let them get into these surface parallel structures is that if in those surface parallel structures, if there's any fine grained material, so like clays or silts, not only, as Jeff said, does it increase the pore pressure, and not only can it act as a driving force, but those fine grained materials, the strength can actually change depending on if they're wet or dry. If you take the clay and run a direct shear test in the lab, but the clay's all dried out and powderized, yeah, you'll get 30-degree friction angle. It looks like there should be no problem. You add a little bit of water to the clay, get it into its plasticity zone, basically make it behave like a plastic. All of a sudden, you have a 15-degree friction angle. So if the situation like just describing, we're well above the water table, maybe normally under normal conditions, these fractures are dry. But if there's fine grain coating on the fractures, we get water in there. We can also have the strength drop just from adding the water alone in addition, which is another, bad factor potentially contributing to slope failures.
Yeah, that's a good point, Scott. I mean, I think Scott and I were looking at an instability last week, which is a fairly prominent instability. It was shallow to the slope and related to the slope parallel fractures and the very things that Scott was describing. So yeah, very important.
Thank you very much, and thank you to our participant for that question.
That's a good question, actually. So yeah.
We have lots of good questions today. All right, I'm going to pull up another from our live group here. And I think first, Scott, maybe I will call on you for this one, if you are willing. So this comes in from Freddie asking, I would like to know, how should we deal with Brazilian tests in the interpretation of Hook-Brown shear strength? In many cases, this data tend to go up I think, okay, let me do that over. In many cases, this data trend tends to raise the properties, and in other cases, lower the values of MI, and I think that would represent sigma CI. So what would you recommend? Was Hook and Brown maybe just proposed for areas where there is compression?
Yeah,
Thanks.
I think I know what that question's getting
Okay.
at.
All right. Would you like to start with that?
Yeah, no, and it is
Thank you.
a funny area. Just because I feel like in the old days, as in old days like 80s, 90s, I think it was more common to try to use that Brazilian tensile data. So basically the measurements of the intact rock tensile strength, to use that to try to fit your Hook and Brown curve. But I think what people have found over the last 10, 15 years is that the Hook Brown envelope, especially for rocks with really low MI values, it'll actually way overshoot that tensile value that you're measuring. So in other words, depending on your MI value, the Hook Brown criterion may not fit that tensile data as well. It might predict, way too strong of a tensile strength, if you will. So I think the most common practice now is to use a tensile cutoff when you're using the Hook and Brown criterion for intact rock. And that tensile cutoff usually will match the actual tensile data better than just letting the curve go off the edge. And then the latest Hook Brown publications in 2019, I think, talk about that a bit if you want to read about it. There was a paper in 2022 by Renani that also discusses it really well. And then there's some good papers by Rob Bewick with WSP that talk about this exact same issue. And he has some recommendations in there that you might need to take your Brazilian data and multiply it by like 0.6 or 0.7, and then it might match the Hook Brown curve better. But I would say, yeah, the most common practice right now that I see is just to fit your uniaxial and triaxial data to the Hook Brown envelope and not worry so much about the tensile data. That's not to say it's not a good data to collect. A lot of times what we'll do in our lab is we'll take a compression sample, we'll cut off the end, we'll do a tensile test on the end cutoff, and then do the compression test on the bigger piece of the sample, on the full piece of core. And what's nice about doing that is now we have something to QA/QC that test with. So if the UCS or the Triax test comes back funny, if it comes back suspicious, if it looks like there could be a problem with that piece of core, now we can go and check the tensile value of the cutoff from when we were trimming that sample to see, well, was the tensile value from the cutoff also strange? Or was it also very strong or also very weak? So it's kind of a good QA/QC check on, was the compression test a good compression test, and was that a good sample? And then if you're running a numerical model, it's also a good idea to do some Brazilian tests, just because when you're running a numerical model such as FLAC, you need to calculate tensile parameters to put into that model as well. So sometimes that data is nice to have.
And could you repeat the paper that you mentioned was a good reference? You said Renani. What year was that?
I can throw them into the chat if that works. I can go find them real quick. And
yeah, I was going to try to
focus on
look in the folder I have and see if it was in there and do exactly that. So
yeah, I can throw some links up.
okay, great.
Mm.
Anyone else on the panel like to contribute to this question? I think Scott did a great job answering that. Thank you for the question, Freddie. All right, and then we have just a comment that I will call out from Zip Savani. Hi, Zip. Saying that weak rock mass strengths can vary broadly with permafrost variation. And I don't know if anyone in the panel wants to comment on that at all with permafrost.
I think that's a good point, Zip. And there's a fairly major failure in permafrost going on at the moment, which looks as though the permafrost has degraded slightly, potentially due to infiltration from the surface, and significantly changed the strength of the rock and the properties of the fault zone. So that's a good point. Changes in permafrost and erosion of permafrost or degradation of permafrost can be a big deal in the Arctic.
right. I'm going to go ahead and pull up another question. Okay. So I'm going to call up Iris for this question. It was pre-submitted, and it is regarding ore deposit types, which was the focus of your presentation for the course. And they're asking of the different ore deposit types, for example, sedimentary, magmatic, metallic, hydrothermal, etc., which are the most complicated or challenging to characterize, do you find, or in your opinion? And if applicable, where do you find that assumptions most often need to be made? And how might that affect the overall understanding of confidence of the future geotechnical model? So it's kind of a large question, but if you'd like to touch on any part of that.
Yeah, that's it's quite a broad question, but I think the big point is the greater the complexity, the more difficult it is going to be to characterize. So for example, if you have a polydeformed metasedimentary faulted deposit, you have lots of factors that could influence the stability. So you're starting off with variability in the initial rock type, and then you have discontinuity for the bedding. And then there's multiple phases of deformation. So you have fold structures, variable fold orientations, and then you have brittle fault structures, potentially a hydrothermal overprint. So you need to go through each of those parameters and define which of them have an impact on the slope stability and which ones you could lump together. So the variability in rock type initially, and then the complexity of deformation. And then on the other end of that spectrum is probably something like an orthomagmatic deposit, where we have one big intrusive body that doesn't change in mineralogical or composition, doesn't have an internal fabric, has very little structural overprint, little alteration. Those are much more predictable and easier to characterize. And the more complex it is, the more data we also need to collect to be able to make assumptions of what's happening in between, of how is each structure type affecting the rock stability, and how are the interactions between rock type and alteration, or rock type and structure affecting each of them. And the less data we have, the more assumptions we need to make. And there's like a balance we have to find between how much data can we practically collect versus how much can we interpolate in between the points and assume that it's going to be the same in between.
Thank you, Iris. Would any of the other panelists like to add to Iris's response for this question? Please feel free to unmute.
I mean, I'll just throw in terms of the hydrogeological component of the geotechnical model, the sedimentary type ore deposits have in addition to the structure and alteration, they have the added dimension of the strata bound or the strata control fractures. And I was just working on a coal mine earlier today, in fact, where the footwall was very thinly bedded, and so there'd been a lot of instability, which was primarily controlled by bedding and water getting into the bedding. So that's when you have a sedimentary deposit or a sedimentary mining situation, then the bedding is something that you have to think about, which you don't with so much anyway with a metasedimentary or a volcanic or an intrusive deposit. But the other factor with the intrusive or volcanics is the alteration, and that can cause a fracture flow situation. If the rock gets altered and weakened, it can change fracture flow to porous medium or dual porosity flow and significantly affect the hydrogeological properties. So you also have to think about the different ore types for the hydrogeological model also.
All right, thanks, Jeff. And while I have you, Jeff, I think I'll pull up another question from our live group. We do have some questions coming in that are more focused on the topic of like numerical modeling. So what we're talking about today is more site characterization models, so understanding what's going on at your site. We will be talking about numerical models coming up when we focus on section 5 of the course. So that will be our next webinar will be on the geotechnical model, and then following that, we'll be talking about the different slope design analysis methods. So if you have any questions on those, you can please reserve those for our future webinars. But I'll bring up just a general question for Jeff to maybe touch on for Emra. What are the biggest challenges in maintaining slope stability while lowering the groundwater level in open pit mines?
Well, I think lowering the groundwater level inherently increases slope stability. I think this question is probably more related to rapid drawdown, and if you have rapid drawdown in a pit, for instance, in a pit lake, it can leave residual pore pressure in structures or in weak materials behind the slope, so you can get an increase in the hydraulic gradient or the pore pressure gradient between the wall rocks and the slope if you rapidly dewater. So I think that's something we have to deal with a lot when we go in and pump out water from lower pits or try and dewater pit lakes. But I think the issue, the general issue with dewatering and slope stability is, as I say, lowering the groundwater table increases the effective stress. So it's always a benefit in the longer term. But yeah, you just have to be concerned that if there are weaker materials close to the slope which don't respond as fast to dewatering as the more permeable units, then you have to worry about equalizing the pore pressure and figuring out how long it takes for the pore pressure to dissipate in those units, particularly if they're close to the slope.
Any other additions from our geotechnical inclined experts here? Not that you aren't, Jeff.
Thanks.
Yeah, I think the key here is if you're worried about rapid dewatering and having slope instabilities because of that, you should probably put in some piezometers, right, to monitor. And then you can lower the groundwater level a little bit, see the response, and then you can actually calculate, well, how long is this thing going to take to drain down? Do we have faults blocking the water off? Are the structures free draining? Do we have low conductivity materials? Whatever it may be. But, this is the case where you probably agree, Jeff, to put in some piezos, do a little bit of dewatering, and don't just go for a rapid drawdown, but monitor it and see what you're dealing with before you jump in too far.
Yeah, good point. You gotta have the piezometers to see what you're dealing with. That's a good point, Scott.
Yeah.
And there's been a number of kind of pit lakes and water in the bottom of the pits that we've had to lower over the years, and sometimes we give them a maximum drawdown rate for the water in the pit, well, in order to allow the pore pressures in the slope behind the walls to dissipate in time. So yeah, it's a contrast between the permeable units and the impermeable units, and those units they're only important if they're close to the slope and therefore create a problem for instability.
And then on the mention of piezometers, just to pull up another question also from Emra, what are the best data collection and calibration methods to improve the accuracy of hydrogeological parameters used in modeling, but I think we could also just say for a site characterization in general. Jeff, what would your response to that be?
So the best data collection methods are cross-hole tests when you have piezometers. So cross-hole tests when you pump or inject or create some hydraulic stress at one location, and you observe the pore pressure change in another location, because I think that then tells you the wider scale impact or the wider scale effect on the hydrogeological system. A lot of people just jump into packet tests, which we talk about earlier in the course, and the issue with packet tests is you're just calibrating the materials in the immediate vicinity of the holes. Whereas if you have a test where you pump or you inject from one hole and you measure the response in another hole, then that is giving you information on the wider flow field and the wider formation. So it's always better to do that. And of course, let's never forget that the open pit actually becomes a large scale pumping test. So if you mine the open pit and dewater the open pit, observations in your piezometers and variations in the behavior of your piezometers around the pit walls will tell you how the different materials respond to dewatering or depressurization, and will be a great method to help you characterize each of the units. So I think the answer to the question is any form of cross-hole testing that characterizes the wider scale formation is always preferable to local scale packet tests or single hole tests. And you can't beat piezometers. Piezometers are the fundamental control. If I think I said that, when I go into a site, the first thing I look at is all the water levels. If the water levels are all similar, we know the hydraulic system is connected. We know it's going to be quite permeable. If the piezometer levels, the water levels are all discontinuous. I'll get it out in a minute. Then we know the hydraulic system is got boundaries and lots of structural control, and the flow system isn't continuous. So piezometers are the fundamental. Piezometers and cross-hole testing is the fundamental method.
Great. Thanks, Jeff. Expert answer as always. Okay, I'm just going to let everyone in the webinar know we have just about 20 minutes left. So if you have any burning questions, please put them in the Q&A now. And I'll remind those of you who are also participants in the course that we have the discussion board available there, where you can post questions throughout the duration of the course availability. And I will make sure to connect you with the presenters to get those addressed. So we're going to switch back to the topic of the structural model. Let me get back there. We'll pull up this one here. So I'll first direct this towards John, and then additionally Luca and Felicia, and then open up to the panel. So this was pre-submitted, and they are asking, well, they're first stating that they understand that major structures and minor structures can impact slope design at different scales, with major structures being more impactful to overall design, while minor structures are more important to bench scale design. So how important is it to always understand both in detail, or should one type be given more attention during structural modeling? So John, would you be willing to start off with this, or I also welcome you to pass on to either Felicia or Luca?
Yeah, I could start off. I guess, in terms of characterization, you have to characterize both, really. You can't just focus entirely on the major structures, have a really beautiful major structural model, and neglect the minor ones, the fabric, because you need that information in order to develop your domain model And so really, I mean, the simple answer is you have to do both. You can't just get away doing one or the other. And it has to be a continuous improvement, progressive characterization. It has to be continually validated and continually improved and continually added to. It doesn't just sit static after you make a first pass or two. You've got to revisit it and have it as a continual progressive characterization. One type given more attention than others, than the other. I would say both are important. And in terms of the stability of the slope in its entirety, the major structural model will, if there's major structures behind that slope, they're going to have an immediate impact, or they could. The minor structures are going to be needed in order to understand the finer detail of the fabric and how it's been domained. I can pass that on to Luca, Felicia, if you have some other comments.
Sure. John, I support what you said. I think you need to focus on both. Getting the major structures can impact your overall and your inter-ramp scale design. And so if you don't get those right, you might have some pretty significant economic impacts. But you also can't ignore your bench scale design and getting your structure domains correct, because there can be some significant risk brought into operations if your bench scale's not right. So you could, for example, be increasing your risk of rockfall hazard and introduce significant costs to the operations down the track if your benches aren't correct. Luca, did you have anything you wanted to add?
No, you both covered everything. I just subscribe everything you said. They really come as a package. There is no distinguishing. It's a package, and especially because major and minor structures, they co-participate in defining the deformational history of an area. So you can actually use the secondary structures to really work out better what happened in that area. And that ties up on, there was a comment or a question in the Q&A session about how we can predict, what is the method to predict shear zones and fault zones. Well, the most advanced method is actually doing your mapping and your interpretation using major and secondary structure, because that will give you the entire overall idea of the structural pattern, the relationship, the geometrical relationship. So sometimes, it's actually the secondary structure that wreak havoc in an open pit, because they might end up controlling fluid flow more than the major structures. They could actually propagate more than what you're expecting, and starting influencing not only bench scale failure but even inter-ramp failures. So it's a package, and they cannot be looked at as separate, and especially because there's always this sort of separation between the geotechnical domaining work and the structural work, but really secondary structure are impacting your joint distributions, and so they go together. So doing an analysis of your minor structure that can help understanding if your structural domain defined by the major structure should be subdomain, because each of the secondary structure actually works as a subdomain boundary as well within your joint systems. So they come with a package. You cannot overlook one in favor of the other one.
Good, and sounds like we have a good expert consensus on this one as well. All right, thank you for that question. Are there any additional comments before I move on? All right, I'm going to pull this question up that is addressed to Scott, and then we will open up to the panel. So Scott, after the development of the initial rock mass model, and with the goal of better calibrating to actual slope performance once mining begins, what would be some indicators that the rock mass strength estimates were too high or too low?
So I guess one indicator that the rock mass strengths were too high is that the slope failed. Maybe you assume too high of a strength and we're having issues. But to clarify that a little bit, if there's a slope failure, the most important thing to do is to properly identify what the failure mechanism was. It's pretty rare to see a slope failure that the entire thing is contained within rock mass, or what we'd call, isotropic rock mass. In my whole career, maybe I've seen that like once or twice. It's not very common at all. What's more common is that we'll see some combination of structures that are in there. We'll see usually pore water pressure involved. And then there may be some parts of the slope failure that are controlled by the rock mass strength. So for instance, if we have a fault that's non-daylighted, maybe the sliding is taking place on a fault and then it breaks through some rock mass at the toe. So if we were to go back, analyze that, and then try to calibrate our model, the challenge with the calibration is that, we may only have one event to calibrate to. Some mines we may have more. A lot of mines we may only have one. But there's usually more unknowns than there are knowns. So we'll have to make some assumptions about the pore pressure. Hopefully we have some good piezometer data. We'll have to make some assumptions about the fault strengths. Hopefully we have some good testing data on that. And then we'll have to make some assumptions about the rock mass strength if that was a component of the failure. So, there are definitely cases where we'll go and we'll collect more data. We'll observe, things that are happening in the pit, and then adjust those estimates up or down, depending on what we're seeing with the actual performance in the pit. An indicator that the strength is too low would be that the estimated factors of safety are very low, but then we're seeing on the radar data, the monitoring data, very, very stable slopes. We're not seeing any issues at all. So in that case, I would advise to do the same thing, kind of go back to the drawing board and, try to recalibrate based on what's being observed actually in the field and the actual performance of the pit.
Go ahead, Felicia.
With regards to rock mass strengths being too low that you estimate, you'll often get some feedback from production. They have difficulty excavating and drill and blast, things like that as well. So it's important to keep that feedback loop between the various teams in the operation.
All right, good answers. Any other additions from our panel? I think Scott and Felicia handled that one very well. Thank you for the question, Sarah. And we have probably time for one or two more questions in this session. So I'll pull up one that was sent for Jeff Beal. Jeff, are there cases where a hydrogeological characterization model is not needed? For example, in an arid environment where there is low rainfall or a deep groundwater table. So Jeff, would you like to comment on that, please?
Well, I think the answer to the question is
I think we've lost your audio.
Oh,
wait.
Can you hear me now?
Yes.
Can you hear me now?
Yep.
Okay.
Very good, thanks.
So I think the answer to the question is no. Hydrogeology is such an important component of open pit mining that you always need a characterization, an understanding, and a hydrogeological model of some sorts. Probably the closest you'll come to having a site with the least important hydrology would be, for example, let's say the Rawhide mine in Nevada, where the water table was 200-300 meters down. It was a significant depth below the open pit. Rainfall was 4 or 5 inches a year, and they had no real problems with leakage from facilities in the pit. But in order to arrive at the conclusions they did, they needed to characterize the system. And then another case or situation I would point to is in, let's say, northern Chile in the Atacama Desert, which is probably one of the driest places in the world, where they have a lot of slope failures related to water, and many of those failures are related to leaky tanks, leaky pipes, uh, leaky ponds, tailings facilities. And so I think the issue of infrastructure is and how that affects the hydrogeology and the slope performance has become a big issue, particularly with pits. And a lot of open pits start off fairly small, and the infrastructure is quite far away from the pit. But then the pit expands and expands, and next thing it's right next to the plant or right next to the tailings facility, and it has to worry about the losses from those facilities. And we spend many of the big mines in Chile spend an awful lot of time and effort and money characterizing hydrogeology purely because of leaking mine facilities. And then another example would be, for instance, in the Sahara Desert, where there's a number of mines in extremely dry environments. But in that case, they'll get a very large rainfall event, maybe once every 2 years, once every 3 years. And if they're not prepared for it, that rainfall event can get into dilated structures. There was an example I worked on where they lost control of surface water around the crest in the crest of the pit in the middle of the Sahara Desert. Pit floor flooded, and the saturation of weak shales in one of the walls caused a fairly significant failure. Anybody who's done the GC water course will have seen the example of that. So the answer to the question is no, but in the climate will very much dictate the type of characterization and the type of analysis that is needed.
Good. And for reference, anyone who doesn't know what he was referring to with the GC water course, Jeff is one of our lead technical advisors for that course and one of our primary presenters. It's a great course you can find on our website, and we'll be releasing the next session in June. So I definitely recommend checking that out if you are interested in water and mine operations and slope stability. And then also, while I have you, Jeff, I'm going to pull up one more hydro-related question that came in from our live group. I know Blair Douglas covered the operational hydrogeology in the course, but I know this is well within your realm of expertise as well. So maybe you could just quickly comment on horizontal drain holes and the recommended depth for installation to achieve optimal results. And then is there a depth behind the slope where pore pressures would no longer significantly affect the integrity of a slope?
So this is topical. Scott and I got into this a bit last week. So it very much depends on the type of failure modes that we're looking at. And if you're and the purpose of horizontal drains, a lot of horizontal drains are used for general dewatering, and if that's the case, you probably want to drill them, as fairly deep behind the slope, 300 meters perhaps. But a lot of holes are, we've talked a little bit earlier about the zone of deformation and the blast damage zone being quite shallow, and a lot of instability related to that zone. And so horizontal drains, if the failure mode is related to the shallow rock mass or the zone of deformation, then the horizontal drains may only need to be quite shallow. And particularly, if you think about civil engineering retaining walls where they pepper the wall with holes, and those holes will never flow except when there's a rainfall event, And the goal of those holes is to relieve the pressure during a rainfall event. Well, the same thing applies to a pit. I think there's more and more mines doing quite shallow kind of pressure relief holes, particularly in slope, in areas where you got, or sectors where you got slope parallel structure. And those holes don't flow except when there is a precipitation event. And the goal is to get the water out of the drains rather than allowing the pore pressure to build up behind the slopes. And there's some pretty good case studies on that now, over the past 2 to 3 years. So the answer is it really depends on the type of failure mechanism. It really depends on what the goal for stabilization is. And there's a couple of slope failures that I've been involved with that have been triggered by drilling horizontal drains that are too deep. And if you're say in a situation where you've got successive slope parallel faults, a danger that you have to think about is if you drill too deep, we can bring water from a deeper fault, which is geotechnically confined and is much more stable, into the horizontal drain hole, and the water can seep out of the horizontal drain hole into a structure which is closer to the slope, less geotechnically confined, and can therefore trigger an instability. And I've been involved in at least 2 slope failures that have been triggered by drilling horizontal drains too deep. So really, the message is you've got to think about what you're trying to depressurize, and you've got to think about the mode of instability that you're dealing with.
All right. Thank you, Jeff. All right, we have 5 minutes left. I'm going to pull up one last question, and we may not be able to cover it in depth, but perhaps our panel can comment on this to some degree. And this question was pre-submitted by Javier, asking about confidence levels in a characterization. And so this is initially addressed first to Scott, but I would welcome any brief comments additionally from the panel. The question is asking how you determine whether a characterization is completed to an appropriate level of confidence for the stage of study, and what do you typically base that on? So again, kind of a broad question, large question, but Scott, maybe you can tackle that one.
Yeah, it's a hard question because it really does depend project to project. So it's really going to come down to what jurisdiction are you working in? Because, SK 1300 or JORC, every jurisdiction will have its own different regulations. So you have to make sure that you're adhering to whatever the local regulations are where that mine is located. It'll depend on the variability that we see at the mine. So some mines, if we drill a few holes and everything is looking the same and there aren't any surprises, for that particular deposit, for instance, it might take less drilling to get to feasibility study than a deposit where we drill a few holes and every single hole is looking different. We're seeing lots of different alteration zones, different types of fault zones, lots of different geotechnical domains. In those cases, we might say, well, we need more drilling to really be at feasibility level for this particular deposit. So it'll really come down to, the mining company's risk tolerance, where the mine's located, and then how the QP on the study or the engineer of record on the study feels and determines what is needed to call a certain level of confidence for an individual pit. And I'll hand it off to everybody else if anybody else has any other comments.
Yeah, I think the only thing I would add to that, Scott, is the consequences. I mean, if you have a situation where there's high consequences of instability, then you probably want to up the ante a little bit with the characterization.
Felicia, did you have something to add?
Yeah, I agree with Scott and Jeff, and would just like to add it's a bit more on Jeff's. It's the risk tolerance of the mining company. Some junior or companies that would like to be miners are willing to tolerate a bit more risk. So it's those types of conversations you need to have and clearly outline the risks that remain. But it's also the how is mining going to progress? Have you got a small starter pit that will give you experience in the slopes versus are you mining ultimate slopes straight away? And so that's very different risk profile, and you likely need a lot more data if you're going straight to ultimate.
Yeah, that's a good point, Felicia, as well. Yeah. How much experience do you have in that particular setting? And benchmarking with other operations, you can get a lot from that also.
Luca?
Oh, I mean, it's just in addition to the risk, is the acceptable level of uncertainties that you like to carry over. That's really it. Because depending on how much you know, you're starting off with a geological and a structural interpretation of the area that has a wider range of uncertainties. And so it comes down to the miner or the QP to feel comfortable in the level of uncertainties and carrying over at each stage of the project.
That's good. And it's also some of the things you guys mentioned are good foreshadowing for future sections of the course. So in section 6, we're going to be covering data uncertainty and design acceptance criteria. And then we'll be talking extensively about risk management in section 8. So I'm sure we'll get into more detail on those topics in both the course and future webinars. But we have reached our time. I'll ask just for any final comments from the panel before I close out the webinar.
There's been some good questions. That's been good.
Yeah, thank you, everyone. So big thank you to all of our panelists here today. We really appreciate you bringing your expertise to the table, as do our students and participants. It's so invaluable for everyone. So thank you so much. We really appreciate you. And thanks, everyone, for joining us today. If we didn't get to your question today, please join us for a future webinar where we will have another great panel of experts, possibly some repeated people that you see here today, and or just post them onto the course discussion board if you are in the course. So hopefully we'll see you again soon, and thank you. Everyone have a great day, evening, wherever you are. Thank you so much.
Thank you.
Thank you, everybody.
Thanks, everybody.
Thanks, everyone.
Great
Yeah.
discussion.
Thank you, everyone.
Bye.
So long.
Ciao.